me tell you, it is truly, truly amazing. Avian anatomy, a comprehensive overview of the biological systems engineered for flight. The blueprint of life, mapping the internal and external structures that make birds the most efficient aerial navigators on Earth. Skeletal framework, strength through lightness. Nomadic bones, hollow bones filled with air sacs reduce weight without sacrificing structural integrity. Yes, bird bones are hollow. That's how come they're able to fly so gracefully. Internal struts, microscopic cross-bracing trabeculae provides reinforcement. The keel, I'm gonna come back to that shortly, but the keel, aka the sternum, is a massive anchor point for powerful flight muscles. Fusion, bones in the skull and spine are often fused to provide stability and power. Let's take a look at the skeletal system of birds. And if you notice, they have very similar bones like us. They have phalanges. We also have phalanges. Okay. They have a sternum, aka the keel. They have a cranium just like we do. They have a femur. Yes, a long bone, the femur. They have a femur also. They have ribs. So as you can see, they have a pelvic girdle. So they have very similar bones like we do. They have the ulna. We also have the ulna. Interesting. Now, this is amazing about birds. Respiratory efficiency. Birds possess the most efficient respiratory system of any vertebrate. Utilizing a system of 9 air sacs, they achieve unidirectional airflow. Unlike humans, air passes through the lungs during both inhalation and exhalation, ensuring a constant supply of fresh oxygen to fuel the high metabolic cost of flight. This flow-through system allows some birds to fly at altitudes where mammals would perish from hypoxia. This is a great diagram of what they're talking about. So the front of the bird would be right here. This is trachea. They have 9 sacs. Okay, 1, 2. They have nine total sacs. So when the bird breathes in oxygen or air, look at this system. Amazing. Unidirectional flow. Boom, boom, boom. Basically, it does this. It basically comes out like that. Amazing. Amazing. The digestive process. The crop. An expansion of the esophagus used to store food quickly before moving to safer environments to digest. For some of y'all who've been around birds or watch any wildlife shows, the crop gets pretty full when the bird starts to eat. Okay? Now, this is interesting also. The proventriculus, the true stomach where chemical digestion begins with the secretion of gastric juices and enzymes. The gizzard is a thick muscular organ that mechanically grinds food, often using swallowed stones, gastroliths, to crush seeds. Now, let's talk about the body mass allocation. Basically, what percentage of what makes up a bird's body mass? On average, by the way, the flight muscles make up 20% of the bird's body mass. The internal organs make up 15%. Now, check this out right here. Remember, I mentioned earlier that bird bones are hollow? So the skeletal system makes up only 5% of the bird's total body mass. Only 5%. Other muscles, 30%. Now check this out. Feathers make up 10% of the bird's body mass. Feathers are twice as much as the actual skeletal system of birds. That goes to show you how light bird skeletons are. And fat and miscellaneous account for 20%. So this is the breakdown of the body mass of the average bird. Okay, now, as a disclaimer, averages are based on typical migratory songbirds. Raptors, which are hawks, eagles, falcons, and owls, may have a higher muscle percentages, of course. Now, the feather variations. Some of y'all look at the birds and think, oh, all the feathers are the same. No, the feathers are not the same. Birds have different type of feathers for different reasons. For instance, down feathers are plumiliferous structure optimized for trapping heat and providing insulation. These feathers keep the birds warm. Flight feathers, obviously, the word speaks for itself. These birds, flight feathers, are responsible for flight. Contour feathers, overlapping feathers that give the birds its aerodynamic shape and coloration. Sensory and neural mastery. Optimized perception. The avian brain is dominated by the optic lobes. They have big eyes, basically, reflecting the primacy of vision. Many birds possess 2 fovea per eye, allowing for high resolution vision in both front and side fields simultaneously. The pineal body acts as a biological clock, sensing light through the skull to regulate seasonal behaviors like migration and breeding. The pineal body. This sound familiar to y'all? Leave a comment below where you heard the name pineal from. Let's talk about the high power engine, okay? The avian hawk. Let me tell you, I've been around hawks, eagles, all types of birds before. And let me tell you, these birds, their heart beats hundreds of times per minute. 100 beats per minute, 200 beats per minute, 300 beats per minute, 400 beats per minute sometimes. Sometimes hummingbirds up to 800 beats per minute sometimes. Birds possess a large, powerful 4-chambered heart to support the massive energy requirements for flight. This complete separation of oxygenated and deoxygenated blood ensures maximum metabolic efficiency. Fun fact, we also have a 4-chambered heart. In hummingbirds, check this out. In hummingbirds, the heart can beat up to 1,200 times per minute during active flight, a feat unmatched in the mammalian world. 1,200 times per minute. My goodness. Let's talk about the biological adaptations of birds, okay? Feature, avian adaptation, and evolutionary purpose. The bone density, nomadic, airfield. The reason for that is reduction of body weight. Lungs, they're rigid plus air sacs. Why? For continuous oxygen absorption. Muscle attachment, carina, sternum keel, powerful anchorage for flight. Waste management, uric acid, cloaca. Water conservation and lightness. Birds do not have, okay, how can I say this? Birds do not have 2 openings like we do, okay? Mammals, humans, we have an anus and we have the urethra. Birds have a cloaca, so do reptiles. The choana is the O, the mouth, and cloaca is the other end. Evolutionary transitions, right? All right, the therapy origins. Development of semi-hollow bones in small dinosaurs. Feather evolution. Simple filaments transition to vein flight feathers. Skeletal fusion. Formation of the sacrum and zygostyle for flight stability. Modern metabolic shift. High efficiency respiration and endothermic regulation. If you have any questions, please leave it below. Hope you enjoyed the insane biology of birds. Birds are truly amazing. Again, I work with all types of birds before: flamingos, vultures, hawks, owls, falcons, gannets. You name it, I worked with them before. And let me tell you, they are very remarkable creatures. And please, next time you look up in the sky and you see a bird, just take a minute and just embrace the beauty of these birds.